Good afternoon, everyone. Today I'm going to be talking about Photonic Integrated Transmitter for free space laser communications, specifically with deep space applications. With his 5 senses, man explores the universe and calls this adventure science. Edwin Hubble, who the Hubble telescope was named after, was the originator of that quote. And humanity, through time, has always been a race of explorers. Early explorers used simple technology like telegraph and later the radio to communicate, and modern satellites use radio communication technology. But the future lies in optics. In order to get the high data rates that new technologies demand, we need to use optics. So they provide greater connectivity, and this right here is an image from an HD video that was transmitted from the moon with laser communication. However, there's issues with laser communication. One you may notice with optics is this screen has been waving for the past couple of presentations. That's due to atmospheric interference between just the projector and the screen. Now, if you can imagine going from Earth to space, those disturbances can be gigantic, and we need to find ways to overcome them. There's also large signal losses over the vast distances in space, but if we can integrate these optical systems, we'll be able to reduce the cost, size, weight, and power of these subsystems. So, this right here is the Lunar LaserCon demonstration. This is the mission that was able to transmit HD video from the moon using discrete optics. And discrete optics are bulky individual components like lasers and modulators that are used to perform these tasks. This is the actual module that did this for this particular mission. And we propose photonic integration that will reduce C-swap. So right here, you can see these dimensions and compare it to these. Also, this photonic integrated chip will consume a fraction of the power of this larger module. So, you may be familiar with standard data communication techniques like on-off keying. It's very simple. When your signal is low, that means you're representing a 0. When your signal is high, that means you're sending a 1. Now, sometimes we're interested in more sophisticated transmission schemes. This one that we're planning on using in our project is called PPM, Pulse Position Modulation. And the idea is that you can encode the information rather than in the height of the wave, in the position of the wave. So if you take your time and you break it up into evenly sized chunks, you can send the exact same signal simply by shifting the position of the pulses. So here in on-off keying, we have a 0, 0, 1, 1, 0, 1. Here, you'll see there's a pulse that's high during the first half of the period. Here, that represents a 0. Again, there's a pulse that's high during the first half of the period. That's another 0. Here, the pulse happens during the second half of this time frame, and that's a 1. So here you have 0, 0, 1, 1, 0, 1. It's the same pattern, just transmitted with a different encoding scheme. Here is 4 ppm. The idea is instead of having 2 sections, you have 4. And if you're not familiar with binary, I've got a table down here that will help you convert. But the idea is the same. You can transmit the signal, same one, 0, 0, 1, 1, 0, 1, with just 3 pulses now, and the pattern continues. Now you may be wondering, and you can go like a lot farther, so that would be fun if we can get over there. Maybe wondering why in the world would this be important? Why would you do this for space communications? And the reason is duty cycle. See, in the on-off keying, half of the time your laser's on. Same thing with 2 ppm. But with 4 ppm, your laser's only on 25% of the time. That means you can be conserving power because you're using it less to transmit the exact same information. And if you get all the way to this 1024 ppm, you could get to less than 0.1% of the time your laser being on. So that means that ppm is very power efficient. So what are we actually doing in the lab? This right here is the schematic for the photonic integrated circuit that we're working with. And it's that little white blob right there. And what we do is we take a ppm signal, put it through electrical probes like Daniel was using in his project. This black blob right here touches this golden electrical contact that's on the PIC. And then from there, the PIC has an optical output that exits through this waveguide and into this optical fiber. The optical fiber then goes to an oscilloscope that gives us our data output. So, experimental setup. So, in order to generate PPM, we need to use a field programmable gate array, similar to what Marco was using in his project. And the idea is that PPM is a rather non-standard signal, and so we need to use a system that you can customly reprogram. As he said, you can change things in the field without having to remanufacture your circuit. So our goal is to generate signals that range from 4 to 1024 ppm. So basically varying the duty cycle in the signals. You can see there's some there, like I explained before. But we also are interested in testing various frequencies. So here you can see the same signal repeated 3 times. And this last one is more stretched out because it's a, quote, slower signal. It's just at a smaller frequency. So in summary, laser communication will support future NASA missions, and photonic integration will be key to lowering C-swap on those missions. Future work will involve debugging the FPGA, generating other modulation schemes that we may be interested in, and testing the next generation of PIC that is currently being designed. Thank you.